Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you a little bit more about smooth manifolds. And just to remind you, what can you do with smooth manifolds? The key point is that you can bring calculus and do calculus on smooth manifolds. And we've seen one notion of this before in a previous video in this playlist, and that's the notion of derivatives. And this notion of derivatives is actually built into the notion of a tangent vector. In fact, you identify tangent vectors with the corresponding directional derivative. So the other thing that you want to do in calculus, of course, is do integration. So what I want to talk about today is the simplest type of integration. That's the integral that you get corresponding to line integrals. And the type of object that we need to integrate corresponding to that are what's called one-forms. So I'll tell you what they are. And I'll also look at a rather interesting application of that. That's the notion of degree that we get out of that. Okay, so for our motivation for defining line integrals on manifolds, I want to look at the usual way one studies this in a several variable calculus course. Okay, so suppose you have some sort of smooth curve like this one here. And let's call it C. And it's given by a smooth map from some closed interval AB to R2, say, like this. That's the first ingredient you need. And the second ingredient is we'll consider some sort of vector field. So this vector field will be defined at least on this C, but it could be more. It could be around on the whole ambient space as well. Okay, so what's the line integral? So in this case, when you have this set up, you can talk about the integral over C, this line integral of v dot d gamma. And one way to define it, although you have to check that it's well defined, is the following way. What you do is that with this curve here, you can look at all the tangent vectors that you get. So at gamma of t, for example, you can look at this tangent vector, and you call that gamma prime of t. Gamma prime of t. The vector field might be something like this, given by the blue arrows here. You can dot this gamma prime of t with the corresponding vector field vector at that point. So that gives you some number. So this is a number which varies with this t, and then you can integrate this function of t. And that's the line integral that you would have seen in your several variable calculus course. Now there's some things to remark about this definition here. It looks like to generalize this definition, you need a notion of dot products. Now, this notion of dot products you do have in the case of Riemannian geometry. So perhaps you might be tempted to think to do this sort of line integral, you need a Riemannian manifold. But actually that's not true, and I'll show you why that's the case. Okay, so let's make some remarks about this setup. So the first thing is that the first ingredient is giving your curve gamma. And one of the things that gamma does for you is it gives you all these tangent vectors. Okay, and that's part of the ingredient to build this definition of a line integral. So what's the other thing? The other thing that you have is the vector field. But actually, if you're more precise, the thing that we're integrating is not just the vector field, it's this v dot. Okay, it's this whole expression here. It's the v, this vector field, but also the dot as well. Okay, so what does that mean? Not just the v, but the v dot as well. You can also see that on this side as well. So really what it is that you input here some tangent vector to this C, and it spits out the number v dot of that gamma prime of t, this tangent vector. So the actual thing that you're integrating, that real integrand, so really what we integrate is not just the vector field, it's the vector field dot. And what that is what you so for each point P on the curve, you input some vector, a tangent vector, and it spits out some number. Okay, so this is the first change in point of view that we have. Okay, is rather than just thinking of this integrand as just the vector field, that's the thing that you try to integrate along this curve, it's actually the vector field with the dot as well. Okay, so for each point P, what is that? So this is actually a linear map from the tangent space at C to R. So in other words, it's just an element of the cotangent space. So this is in TP star of C. So what we're going to do to integrate on an arbitrary manifold, one that doesn't necessarily have a dot product, in other words, a Riemannian metric, is we're going to absorb the dot product into the integrand. Okay, that's the way we'll do it. That's the idea. Okay, so let's see how that works, and that comes to the notion of what's called a one form. Okay, so motivated by this setup, we come with the definition now. Suppose X is some smooth manifold. Okay, so what's a one form? So before, what we had was for each point on this curve, we gave a vector. Okay. So what you have now is, instead of having a vector, so something maybe in the tangent space, what we have is something which is a linear functional on the tangent space. So this is going to be a function from x, so we pick a point P on side x, and you map it to something that's, rather than a tangent vector, is a cotangent vector. So an element of T star P of x. And that's the definition of a one form. Now that we've defined one forms, which are the objects that we integrate, let's see how we define the integral of such an object. Okay, so as before, we're going to consider some oriented curve inside our smooth manifold X. So gamma is going to be a smooth function from some closed interval a, b to c, like this one here. And then you consider a one form, omega, which sends every point P to some cotangent vector, omega p, and we want to define the integral along C of this one form omega. And we'll use the same definition that we had before for the line integral, but rather than using the dot product, what we're going to do is we're going to pair the tangent vector with the one form. Okay, so before we did the dot product of two tangent vectors, now we just pair it with one form. Okay, so let's look at the tangent vectors. The curve, of course, gives you all these tangent vectors, so you have this gamma prime of t. This will be a tangent vector at the appropriate point, so here it will be at gamma of t. So now you can pair that with a linear functional on the tangent space, so that's omega. Here the p is gamma of t, omega gamma of t, and so this gives you a number. And this is a number for each value of t, that parameter t. So now you get a real valued function of t from a to b, just as you did before. And then you can integrate that. And that's the definition of the integral of this one form. So you see here, we really didn't need that notion of the dot product, that Riemannian metric, to make this definition work. The only thing we need to do is now realize that the object that we integrate is this one form. So it gives you cotangent vectors for every point instead of a tangent vector. Okay, so one thing that's very important is that really this line integral should depend on the curve and also the orientation. So you have to know that you start here and you end here. Okay, so if you reparameterize, the question is, do you get the same answer? And the answer is yes. Okay, so suppose we change the parameterization so that t is now a function of u, and u is the new parameter. Okay, so the definition of the line integral, if you use u instead, is the following. Okay, so you use omega gamma t of u, and you pair it with this d gamma du now, the tangent vector with respect to u, and that's du, that's the thing that you integrate, so that's the integrand, that function of u. And the point is that, well, you've got the usual change of variable to compute this derivative, so d gamma du can be expressed as d gamma dt times dt du. And the point is that, well, for each t, remember, this is a linear function of what goes on here. Okay, so it's a linear function. So for each value of t, this is just a scalar. And so you can pop the scalar out, and when you pop that scalar out, dt du, the dt du is just, of course, equal to the differential dt. So this is independent of the choice of parameter. And that's also the reason why you want this to be a linear function from the tangent space to R, not just any old function. Okay? You can define it if this was any old function from the tangent space, so you input tangent vectors and come up with a real number, but the linearity gives you this independence of reparameterization. Okay, so that gives you the definition of a line integral for an arbitrary manifold. Okay? And the key thing to realize is that you need a one form for it. Let's look at a simple example. So this one's fairly basic, and it's not too interesting, but it gives you rise to lots of important phenomena. Okay, so suppose we have a smooth real valued function on x. Okay, the set of these will be denoted C infinity x. then of course one would expect that df should be some one form. Okay, it's a differential, and it is actually a one form. And let me show you how that is. And in fact, we've actually seen that before. Okay, so that means to each point you have to give a cotangent vector. So let's pick a point P. Okay, so it might be a point on the C, for example. Okay, and dfp should do what? It should be a linear map which sends the tangent space to the reals. Okay, so if you input a tangent vector, you should get a real number. Okay, so let's suppose we input a tangent vector, and I'll call it d nu because I want to think of this as a directional derivative. Okay, so you have a directional derivative at p, which corresponds to a tangent vector. Then how do you get a number out of that? Well, what you can do is you can look at the directional derivative of f in the direction of nu, and that will be the number that you want. Okay, so this is certainly a linear map from the tangent space to reals, and that gives you a one form. Okay, so let's just look at this and see what happens when you try to integrate this one form. Okay, so that's easy enough. So you look at the integral, say, of df along C. Okay, it's something we can integrate because it's a one form. And what do we have to do here? We have to use this formula here. Okay, so what you do is you rewrite this as an integral of a function of t. Okay, so you parameterize it. So of course here, let's suppose the curve is the same one here. And you have to pair this one form, so the dfp, with these tangent vectors. Okay, and that's the integrand as a function of t. So you want to pair this dfp with the tangent vectors, nu. And what are the tangent vectors to this curve here? Okay, they're these gamma prime of t. So basically, you want to take the directional derivatives to pair it. You take the directional derivatives along this curve. So what you're actually integrating is you want the directional derivative of f along the curve. So you evaluate f along the curve, gamma of t, and you differentiate. And then this is the thing that you want to integrate from A to B. And what's interesting here is that, of course, well, you're integrating a derivative, so of course the fundamental theorem of calculus tells you what that should be. Okay, it's this composed function, f composed with gamma, evaluated at the endpoints, and you take the difference. So it's f of gamma of b, so it's the f value at the end of this curve, minus the f value at the beginning. And that's kind of what you expect. So this is the differential, and if you want to integrate this differential, what do you get? You integrate along this curve, you get f of one endpoint, the endpoint, minus f of the starting point. And that's exactly what you expect. Okay. So the next thing that I want to introduce is the notion of when a one form is smooth. So of course here you don't get any really interesting integrals, okay? So what other things can you do to get an interesting integral? So for example, this is a one form. So at each point you get some cotangent vector. And what you can do is at each point you scale it by a certain amount to get a different cotangent vector. So you could scale it by a different amount for each point, so you can basically multiply it by a function. Okay, so you can consider fidgi, and that's going to be a one form as well. And similarly, you can take sums of these sorts of things. And if these fi and gi are smooth functions, then this is what's called a smooth one form. So smooth one forms are those which locally have this form. They're the sum of fidgi, where the fi and the gi are both smooth functions. To get a better understanding of these one forms and tangent vectors, it's often good to have a look locally at what's going on. So what I want to do now is to give a local description of these tangent vectors and cotangent vectors. Okay, so to do that, we'll consider a smooth manifold X, and we'll just pick a chart. The chart will give us an open neighborhood of any point that we like. So we'll just pick one chart. Phi is going to be a homeomorphism from the unit n ball Bn to some open subset V of X. So one thing I want to do is to introduce the functions on this V here. And the way we'll do that is by using functions on Bn. So there's some natural functions here that we can induce functions over here. So the function xi, that's a coordinate function, the ith coordinate function. What do? We start with V and we move back to Bn. And on Bn we use what function. So firstly, this is the unit ball inside Rn. And inside Rn, what we can do is we can just pluck out the ith coordinate. So we project onto the ith coordinate, and that ith coordinate is going to be some real number. Okay, so that's how I get a function on V. So this open subset of X, a function from V to R. Okay, so let's have a little look and see a picture which might capture how you should think about this sort of situation. And I'll just do the case where n equals 2. So the manifold here will be some sort of a surface. Okay. So it'll be a surface like this one here. Okay, you can look at the image of the 0 vector inside here. Okay, that's 5, 0, 0. And then you can look and see, for example, where x1 equals 0. So x1 equals 0, there are 2 coordinates, so x2 can change. So as you vary x2, you'll move along like this. Okay, so this is a level curve where x1 equals 0. Instead, we can look at where x2 equals 0, and by varying x1, you'll move along this level curve like that. Okay, so let's consider the tangent space at P, where P is just phi of 0. So the tangent space to this point here, okay, what does it look like? Okay, so I guess we're looking at equivalence classes of trajectories. Okay, so one trajectory, of course, is along this level curve where we keep x2 at 0, and we move the x1. More generally, the trajectory that we have is we move the x1, so we look at 5. T, this is going to be the time parameter which can move, and we keep all the others fixed. Okay, so we move along a line like that. Now, of course, if this was actually in Rn, so this is just the identity here, this is just Rn, we're keeping all the coordinates except the x1 fixed, and the corresponding directional derivative when you move along this trajectory is, of course, just the partial derivative with respect to x1. Okay, so the directional derivative along this trajectory will record using this symbol here, d dx1. Okay, so here, that's d dx1. So similarly, we can hold as many coordinates as we like fixed, or all but one of them fixed, and move that the remaining coordinate. So here we can keep x1 equal to 0 and just change x2, and we get d dx2. And more generally, this works for n-dimensional manifolds. You get d dx1 all the way down to d dxn. Okay, so that's what's going on here. And then you may ask, well, what's a dual basis to that? So here's a vector space, and here's a dual vector space. So you can ask, what's the dual basis to this? And I hope you can guess what that has to be. Of course, we came up with some one forms before, okay, and their corresponding cotangent vectors. So it's going to be dx1p all the way up to dxnp. Okay, so dx1 up to dxn, so x1 up to xn are smooth functions, okay, almost by definition, okay. So you can look and see what are those one forms at the point P, and that will give you n cotangent vectors. So the dimension of this is going to be the same as the dimension of this, which is also the dimension of the manifold. Okay, it's going to be n. Okay, and that gives you a nice local description, and it emphasizes the duality between these tangent vectors and these differentials that you see here. So another thing that is good to note when we're looking at these local coordinates is that it allows us to express general smooth one forms quite nicely. Okay, so if you have a general smooth one form, it's based on things like which look like df. And of course, you can use calculus and the form for a differential to rewrite this in terms of the coordinates. So it looks like something like this: f1 dx1 plus all the way down to fn dxn, where these fi's are smooth functions. And so if you add multiples of these together, then actually you'll still get something of this form. So every smooth one form, you can, once you've picked coordinates, you can give a nice form for it. Okay, it's just this linear combination of these differentials, dx1 up to dxn, where you multiply by smooth functions outside. Okay, and this gives a nice local description for one forms, tangent vectors and cotangent vectors. So the last notion that I want to talk about is a very, very important geometric concept known as the degree, and I want to show you how you can relate this concept to one forms. Okay, so the degree is something which concerns spheres, and the simplest case will be the one sphere. So S1 is the circle, And the way I want to think about this circle is just as the set of complex numbers with modulus 1. Okay, so here's my S1 here. And one of the things that we have is a multi-valued function on the set of complex numbers, and I'll restrict it to this S1. So this multi-valued function is theta is the argument of z. Okay, so for example, if you have a positive real number here, so the 1 here, the value here could be 0, but it could also be 2 pi, 4 pi, minus 2 pi, and so forth. So it's multi-valued in that sense. Okay, and in general, the angle theta is just this angle here. So with this multi-valued function, of course, you can't immediately get some sort of one form. But the key point is that if you pick any real number, you can get a single valued function out of this. So how do I do that? So suppose I pick some sort of real number alpha corresponding to this angle here. And then I look not on the whole of the circle, but on that part of the circle where I remove this e to the I alpha. Okay, then I can look at the arguments which land in the interval alpha up to alpha plus 2 pi. Okay, so that now is a single valued function because we force the argument to be inside this interval of length 2 pi. Okay, and it's well defined on this open subset of S1. So since it's a single valued function, and it's clearly smooth as well, okay, so we can talk about the differential d theta alpha. Okay, so this is some one form that's defined on this open set everywhere except for at this point here. Okay, so what we want to do is we want to extend it to get some sort of one form on the whole of this circle. Okay, and the way we'll do that is that we're going to define it here. We're going to actually define it on some open neighborhood of this point here as well, such that it agrees with d theta alpha on the other side. And how do we do that? Well, what we'll do is we'll just pick another point alpha prime here. And we can consider d theta alpha prime. And this is defined everywhere, okay, except for at e to the I alpha prime. And the key point is that these two are actually equal where both of them are defined. So away from this alpha and this alpha prime, this e to the I alpha and this e to the I alpha prime, they are actually the same. And why is that the case? Because remember, what is theta alpha and theta alpha prime? They're just arguments. Okay, you're just taking the argument of points here. Okay, so if you take the arguments of points along here, what do they differ by? What could be the possible difference? The only possible difference is some integer multiple of 2 pi. And that integer multiple of 2 pi, of course, has to stay constant on this connected component here and constant on this connected component here. Okay, so even though theta alpha doesn't equal theta alpha prime, they'll differ by some integer multiple of 2 pi on this bit here and some integer multiple of 2 pi on this bit here. The point is that on the connected components, they differ by constants. So when you take d of them, they're actually the same. Okay, so as differentials, these are the same where they intersect. So now I can use the common values, or the values of d theta alpha here and d theta alpha prime here, to define this one form on the whole of this circle. And remember, to check smoothness, that should be a local criterion. Now this is a smooth one form, so it's smooth everywhere away from this point here, and this is smooth everywhere away from this point here, so that means that this is smooth everywhere. Okay, so the upshot of all this is that we now have a smooth one form on S1, and we'll just call it d theta. Okay, so the d theta is just equal to d theta alpha, where d theta alpha is defined. And this is for all alpha, so it doesn't matter what alpha you pick, you can use this as a definition. Yeah. Okay, great. So now we have an interesting one form defined on this circle. Okay, so with one forms we can integrate. So let's have a look at the integrals of some curves, some line integrals of this one form. Okay, so we'll consider a curve gamma from AB to S1. And we'll look at a simple case first. So the simplest case is where this curve doesn't wrap around the whole circle. It always misses some point, like e to the I alpha. Okay, so I guess it misses this point, so maybe it starts over here like this. So here's gamma of A. Starts here, and it goes around, it can come back, and it can go around and come back, and it ends up somewhere like here. Okay, so there's gamma of B. Okay, ends up there. But it doesn't ever touch this point here. Okay, so let's see what is the integral of this one form d theta along gamma. Okay, so the point here is that, well, this d theta, as far as this path is concerned, you can replace it with d theta alpha because you never go through this point here. So you can replace d theta with d theta alpha. And then we can integrate it using the formula that I gave before, which is the one suggested by the fundamental theorem of calculus. Okay, you just evaluate theta alpha at the endpoints and subtract. So it's just theta alpha of this gamma b here minus theta alpha of this gamma of a. So basically it's just how much you've rotated in going from A to B, how much you've rotated anti-clockwise. Okay, that's what this value is here. Okay, so now suppose instead we have a curve which is closed, so it starts and ends at e to I alpha, so it starts and ends here. But the rest of it is inside this bit here, okay, so away from this point. And let's suppose we shoot off in this direction, okay, so you can move off as you like and go around, and eventually you end up here, okay. So what's that integral? So I guess the key point is that, well, this should be continuous. So if you have a path which approximates it very closely, maybe we just chop off the bit of the beginning and a bit of the end, then you're very close to this bit here, and then you move all the way around to here, okay? So it's almost 2 pi. And as we decide to chop off less and less, the limit that you get is going to be actually 2 pi, okay, if you go around in this direction. If you go around in the opposite direction, of course, you'll get minus 2 pi. Okay, so in this case here, the path wraps around the circle once, and this integral is going to be something that's interesting now. It's going to be plus or minus 2 pi. Okay, plus or minus 2 pi. Plus if you go around in this anti-clockwise direction, and minus if you go around in the clockwise direction on the whole. Okay, so in the middle it can go back and forth. Okay, but at the end of the day, if it's really going around in a clockwise or anti-clockwise direction, that will give you the sign here. Okay, so that should tell you also more generally what happens if you have a closed curve. Suppose instead you wrap around this several times. Okay, then what is this line integral? Okay, so if gamma is a closed curve, then of course, as you can see from this argument here, the integral of d theta over gamma is 2 pi times the number of times you wrap around this circle in the anti-clockwise direction. Okay, and that number of times that you wrap around the circle in the anti-clockwise direction in total is called the degree of gamma. Okay, so this is telling you about the degrees of basically closed curves on S1. And what's a closed curve on S1? To get a closed curve on S1, that means you map an interval to S1 where the endpoints map to the same place. So it's basically just a map from S1 to S1. So given a map from S1 to S1, if it's smooth, you can talk about the number of times it wraps around the circle, that's the degree. And one way to define it rigorously is to use this one form here, and it ties in nicely with this notion of integrals and line integrals of one forms. I hope you enjoyed this adventure in pure mathematics.